Hey guys, I'll be discussing the diagonal relationship of lithium and magnesium. So here I'm mentioning the similarities of lithium to group 2 elements. So lithium does not form an isolatable hydrogen carbonate, whereas solid hydrogen carbonate salts can be obtained for the other group 1 metals. Solid hydrogen carbonates cannot be isolated for the group 2 metals. Lithium salts tend to be hydrated, often as trihydrate, whereas the salts of the other group 1 elements tend to be anhydrous. Many group 2 metal salts are hydrated. Three lithium salts, carbonate, phosphate, and fluoride, have very low solubility, unlike the salts of the other group 1 metals. These anions form insoluble salts with the group 2 metals, and lithium is the only group 1 metal to form nitride. The group 2 metals all form nitride. So all four of these properties can be attributed to the significant difference in ionic radius between the large typical group 1 metals and the significantly smaller lithium ions. So some specific similarities of lithium to magnesium. The only tricarbides of group 1 and 2 elements are lithium carbides and magnesium carbides. Many lithium salts exhibit a high degree of covalency in the bonding, as do those of magnesium. Lithium formed organometallic compounds similar to those of magnesium, and lithium is believed to occupy the same receptor site as magnesium in the treatment of bipolar disorder. As with the nitrides, the formation of tricarbides can be interpreted in terms of stabilization by higher charge density cations. The covalent behavior can also be explained as a result of lithium and magnesium being higher charged density cations than the other members of their respective groups. So based on this article that I read, they reproduced the reported synthesis for lithium and magnesium cyanurate in order to elucidate if the diagonal relation prevails under these conditions, or if the general trend of the higher the charge to radius quotient is, the more hydrated the cation becomes. They reported the synthesis and the crystallographic characterization of lithium and magnesium cyanurate, two compounds both featuring dihydrogen isocyanurate anions. So here I included the crystal structure of magnesium cyanurate. So in magnesium cyanurate represents two different magnesium cations are coordinated octahedral as seen in figure 1. These magnesium hydroxide complex form closest packed layers in coplanar orientation to the crystallographic AC plane with the B lattice parameter, a distance between the cationic layers as seen in figure 2. Together with two additional non-coordinating water molecules within these layers, a two-dimensional network of hydrogen bonds is formed in a way that magnesium hydroxide octahedra becomes hydrogen bonded to 6 water molecules, whereas each one of the non-coordinating water molecules is involved in 3 hydrogen bonds. In between those layers, dihydrogen isocyanurate anions form planar ribbons, as seen in figure 3, running nearly parallel to the crystallographic C-axis. A further stabilization of the anionic ribbon as well as the cationic layers results from the additional hydrogen bonds between the lone pair electrons of oxygen and deprotonated nitrogen atoms of the hydrogen isocyanurate anions with hydrogen atoms of the coordinated bond water molecules of the complex magnesium hydroxide cations. In total, a 3-dimensional hydrogen bond network with distances and angles typical for this kind of compound results, which is able to stabilize hydrated magnesium cations in layers as well as dihydrogen isocyanurate anions in ribbons within the crystal structure of magnesium cyanurate. The crystal structure of lithium cyanurate also shows hydrated lithium cations and infinite ribbons of hydrogen bonded dihydrogen isocyanurate anions, but unlike magnesium compound, the isocyanurate units here are literally involved in the coordination spheres of the lithium cations. The more complicated cationic substructure of lithium cyanurate shows 3 crystallographically different lithium cation positions with different coordination patterns. Lithium 1 is coordinated by a triangular bipyramid of 5 oxygen atoms, of which 2 also form the equatorial plane of the bipyramidal complex unit, belong to the carbonyl oxygen atoms of dihydrogen isocyanurate ions, while the other 3 are part of water molecules Lithium 1 and lithium 3 are with about 100 pm distance, very close to each other, and exhibit next to the identical tetrahedral coordination patterned by 3 water molecules and 1 cyanurate anion represented by an oxygen atom, but both lithium cations positions are half occupied. So they concluded that owing to the strong tendency of magnesium hydroxide cations to become maximally hydrated, as indicated by the high charge to radius quotient, magnesium cyanurate contains octahedral magnesium hydroxide cations as well as more than 4.5 times the amount of water as found in lithium cyanurate and twice the amount than in other isocyanurate compounds containing only one type of alkali or alkaline earth metals. Thus, the diagonal relationship between lithium and magnesium is overruled by the hydrophilic character of magnesium hydroxide cations, but the coagulation of the hydrogen isocyanurate anions to ribbons by means of 2 times 2 nitrogen-hydrogen bonds for each one remains the same as observed in the most other monobasic isocyanurate hydrates.